In the fourth part of the lecture, we're going to have a look at an example. A long, thick-walled cylinder. Here, we have a long cylinder constrained along the z-axis. So the z-axis is strain-free. You see it here. The long cylinder, it has internal pressure, outer pressure, and the main axis. The longest axis of the cylinder is aligned with x3 or z direction, and it is constrained between two walls. This is basically the case of a long tube or a long cylinder, like as we've seen before, the long airways, the blood vessels. So because of the long dimension, we can assume there is no axial strain there. So it's going to be the plane of the case of plane strain. The cylinder is subject to constant external PO and internal PI pressures, and there are no body forces. So V is equal to 0. Let me explain the case of plane strain a little bit more. We've already seen that, for example, if we have a cube, and we push it from two sides, it's gonna shrink from that dimension, but also expand in the other dimension because of Poisson's effect. Okay, so we're gonna get a displacement on the other direction. But assume that we have the same cube under compression, but this time we have two fixed walls on two sides of the cube, so it cannot expand in that direction anymore. Okay, in our case, our cube is hollow, so when it shrinks from one dimension, it basically causes a further shrinkage in the internal hole. The reason is if the density of the material is constant and you push it from one dimension but you don't let it expand in the other dimension, the hole at the center will be occupied by the extra material. So basically you're gonna get a smaller hollow in the center of the tube as a result of that constraints on both ends. But you see that there is no deformation on the direction of constraint. So to explain these cases, we can actually have a look at the cross section of the tube and cut a very thin plate. If we cut a very thin plate here and have a look from the direction of the axis, we can see the internal hole, the outer area, the internal pressure, outer pressure, and we can define that as a plane strain problem in cylindrical coordinates, with z-axis perpendicular to the plane of this thin plate, x1, the first direction, equal to r, the radial direction, and x2 equal to theta, the tangential direction. This is a plane strain problem that satisfies the governing equation for axisymmetric stresses and displacement in cylindrical coordinates. We've already seen why it's a plane strain case. We've already seen why it's cylindrical case. But again, since the pressure PO and PI are symmetric and the cross-section is axisymmetric as well, so the pressures are axisymmetric, the cross-section is axisymmetric as well, so we can say the whole problem is axisymmetric. As a result, we can use the set of relations we found for axisymmetric cylindrical case to solve this problem. Okay, let's see if we can further simplify the equations that we have. We're going to have a look at the displacement field from the equations that you've seen in the previous sections. But since it's axisymmetric case, it means displacements have no dependency on theta. So basically everywhere that we have a dependency on theta, the constant should be 0. We have C1, C4, C5 here, and we have C4 and C5 here. Okay, anyway, we had only C4 in the equation for phi, and we didn't have C4, C5, or C6 for the equations for the cylindrical stresses. But at least it helps us to cancel C1 completely. So as a result, our equations are now even simpler. Now that we have a simpler and even simpler set of equations for the cylindrical stresses, we're going to work out the rest of the constants from the boundary conditions. Here we have 3 boundary conditions. One is on the inner surface, one is on the outer surface, and one is just the axisymmetry. So, for the outer surface, at r equal to rho, we get the stress to become sigma rr to become equal to minus PO. Basically there we have attraction equal to minus PO 0, 0, and the normal there is in the direction of the radius. So basically the traction is in the opposite direction of the radius, but the normal vector is in the direction of the radius. Okay, we just simply use traction equal to sigma ij and j for j equal to r, theta, and z here. The Cauchy stress formula to find sigma rr. For the inner tube, the pressure is along the radius, so the traction is pi 0, 0. but the normal vector is toward the center of the circular cross section. So the normal is -1, 0, 0. This time again using the Cauchy stress formula, we get sigma RR equal to minus pi. Okay, we've already found the set of relations for stresses in cylindrical coordinates and simplified it due to axisymmetric displacement, so we don't have C1 anymore. Let's find sigma RR at the boundaries. For the case of R equal to RO, we get sigma RR at RO is minus PO, and we just substitute R equal to RO into sigma RR relation, and we get 2C2 plus C3 multiplied by 1 divided by RO to the power of 2. And you see that there is no C1 there. For R equal to RI, sigma RR at R equal to RI is equal to minus PI, and substituting R equal to RI in the relation for sigma RR, we get 2C2 plus C3 multiplied by 1 divided by RI to the power of 2. Okay, let's subtract these two equations. We end up with, and we just bring RO and RI, we multiply everything with RO square and RI square. We end up with RO square PO plus RI square PI equal to 2C2 multiplied by RO square minus RI square. So from here, we're going to find that C2 is equal to PI RI square. Okay, let me write it better. C2 is equal to PI RI square minus PO RO square divided by 2 times RO square minus RI square. That's C2. We can substitute C2 in one of the equations above and solve for C3. As a result, C3, so basically substitute C2, we end up with C3 equal to minus RO square PO square minus 2 RO square PI RI square minus PO RO square divided by 2 times RO square minus RI square. Okay, you immediately see that we can cancel the 2's here, But then we have to multiply everything with RO square minus RI square, and then we can even cancel further terms, and finally we end up with C3 equal to RI square RO square multiplied by PO minus PI divided by RO square minus RI square. Okay, we found C2 and C3, and C1 was 0. So if we substitute for C2 and C3 in the relations for stresses in cylindrical coordinates, sigma RR, sigma theta theta, and sigma ZZ, we end up with these three equations. Pay attention that we found sigma RR and sigma theta theta as a function of R only. It's not these relations are not functions of theta because it's an axisymmetric case. And also we found them based on the internal and external pressure and radii. Okay. You may remember that we could solve the same problem from Laplace's law by just assuming that imaginary cross-section. Let's see the difference between this more accurate approach and that more simplified approach by actually plotting the values for the stresses. Here we plotted the values sigma theta theta and sigma RR, basically the radial and circumferential stresses as a function of R, the radius, for two different cases. The plots are drawn for RO divided by R equal to 3. So when RO is 3 times RI. And also compared for Laplace's solution for the circumferential stress. You see them in red. Okay, let's have a look at the plots on the left side. It's for the case that we have only internal pressure. So basically PO is 0, the external pressure is 0. You see that the radial stress on the outer surface, where the pressure is 0, is almost 0. And both the radial and circumferential stresses get to a maximum value as we move toward the inner circle. Obviously, I'm talking about maximum absolute value. So basically, sigma RR, depending on the definition of the cylindrical axis, sigma RR tends to become minus, sigma theta theta tends to become positive. So basically, sigma RR divided by P, they have a negative relation, but sigma theta theta, they have a positive relation. But let's focus only on the absolute value. So both of them have minimum value on the outer surface where the pressure is 0, and both of them get to a higher value as we approach toward the inner area, inner cavity. For the case that external pressure, we have only external pressure, so PI is 0, the internal pressure is 0, we have the plots on the right side. This time you see that sigma RR, the radial stress, is 0 on the inner surface, where the pressure is 0. But still you see that we have circumferential stress there. The difference here is, in this case, we have the maximum radial stress on the outer surface. But again, we have the same as the previous case for the circumferential stress sigma theta theta, we have the maximum again on the inner surface. So basically, it doesn't matter if we have only internal pressure or external pressure. Circumferential stress sigma r sigma theta theta will have a maximum value on the inner surface. But depending on the case that we have higher internal pressure or external pressure, sigma rr may have a maximum either on the inner surface or on the outer surface. The other thing to pay attention is the Laplace solution. So you see that the Laplace solution doesn't predict any variation in the stress along radius. And it's equal to the average of the circumferential stress calculated from our area stress function. Again, you see for the case that we have only external pressure, the mean value of circumferential stress, or the Laplace's circumferential stress, is higher than for the case that we have only internal pressure. So basically, the circumferential stress is higher when we have higher external pressure. And also, again, let me tell that the Laplace's solution for circumferential stress, sigma theta theta, remains constant throughout the wall, and it's like the average of the actual value. So it's basically smaller than the maximum stress, and it's higher than the minimum stress. So it shows that it's better to use Laplace's solution only for thin walls, where this variation is not significant. But for thick wall cylinders, it's better to use the more precise solution based on area stress function. That was it for today. As summary, we've derived the governing equation for isotropic plane stress-strain theory in cylindrical coordinates and in terms of area stress functions. And also, we've used these equations to solve a pressurized thick-walled cylinder.